Children, conservation laws for nuclear reactions. What things might we conserve in a nuclear reaction? Normally energy is conserved. Nuclear reactions are,
they're just a bit crazy.
They're one out of the box. We have, rather than energy, we have mass energy is conserved. And so that's this idea, which we'll come back to more later on, that mass and energy are like the same thing, kind of seen through a different lens. And what Einstein puzzled out is that we can convert energy into mass and mass into energy. And the E equals mc squared equation gives us like a measure of how that conversion happens. So the C is the speed of light. And so c squared, speed of light squared, big number squared is like a really gigantic number. So the E equals mc squared. E equals mc squared lets us work out an energy equivalent for mass. And so in a nuclear reaction, the energy and the mass, kind of add those quantities together, thinking about making the mass into an equivalent amount of energy, that mass energy is going to be conserved. But during a nuclear reaction, mass is converted into energy, or energy is converted into mass, so that the amount of each does not stay constant. Other things that might be conserved in a nuclear reaction. Momentum is always conserved in nuclear reactions. What else? Two more things that we can conserve in nuclear reactions. Oh gosh, okay. Number of nucleons. What's a nucleon?
A proton or a neutron.
Proton or a neutron. So the number of particles stays the same, and charge number is conserved. We can't create charge, we can't destroy charge. So charge number is conserved. Four things. The mass energy is conserved. We're going to use that later on in this topic to do some calculations about how much energy is released in a nuclear reaction. Momentum is conserved. It's something you're going to use probably later on in your physics career when you come to analyse like collisions of subatomic particles, and you can use conservation of momentum to kind of puzzle out what's going on. This year, for solving nuclear reaction problems, we're going to use conservation of number of nucleons and conservation of charge number a lot. Example. Polonium-210 decays by emitting an alpha particle. What's the thing that's formed? Who can conserve nucleon number? Which one's nucleon number? Top number, bottom number?
Top, so it would be 240. Oh no.
Not
it would have
240.
been 206.
Nice. 206. Who can conserve charge number?
82.
82. Does everyone see how that's happened? That something plus 2 must be 84. What? 82. Something plus 4 must be 210. What? 206. What's the thing? What's 82? Lead. And so what's happening in our alpha source as it decays? What are we going to end up with? What's it mostly?
Lead.
It's mostly lead, and helium gas will have been formed kind of around it as those alpha particles come out and ionize those few centimetres of air. Once they've grabbed 2 electrons and become a helium atom, helium's a non-reactive atom, so it just kind of floats up into the atmosphere. Iodine-131 decays by a beta minus emission. Let's try and write down a nuclear reaction for that together. Iodine-131, how am I going to write iodine-131 as a nuclide? With nucleon number and charge number and symbol. What do I write for iodine?
131.
53. Cool. And then it decays by emitting something.
So you go and then do B.
So same as we do for chemistry, the arrow indicates a reaction happening, and the arrow shows us the direction of time, I guess, like the reaction happened. It's this way. We started off with this, like the mother nucleus, and we end up with the daughter nucleus. How can I write beta minus using nucleate symbols?
Is it just B and then 0 on top and negative 1 on the bottom?
It's a beta 0, negative 1, plus, what's the other thing that's formed? What do we know about its nucleon number?
131 on
It
top.
must be 131,
And then 54 on the bottom, surely.
and it must be 54 on the bottom, because 54 plus negative 1 is 53. What must it be?
I can't pronounce that. Starts with an X.
Xenon.